Okay, we're looking at starting chapter 4, and it deals with probabilities. So we need to discuss what are probabilities. And so we run across in everyday language, what is the chance of, something occurring? So like, the chance that we'll get rain, there's a 65% chance you're going to get rain today. So when we're talking about probabilities, the way we would say that is there is a 0.65 is the probability of rain today, or there is a 0.65 probability of rain today. So um, it's a way of talking about chances of things occurring in a slightly more mathematical way. So what is the chance of it not raining today? If there's a 65% chance of rain, that means there's a 35% chance of not getting rain. Or in other words, the probability of it not raining today is 0.35. And so we'll come back to this idea of this happening or the not it happening later in this video. Um, okay, so let's say we did this. Sorry, you can't really read all that, but relative frequency of student ages at a community college was this. Somebody did a kind of a study, or maybe they just collected the data that they have at the college, and they found out, the relative frequency 0.03 or 3% of the students are younger than 18. 0.30 or between 18 and 19, or 30% are between there. 35% are between 21 and 21. 20 and 21, 25% are 22 to 23, greater than 23. So, if I said, let's say you met somebody at this particular college, and we asked you some questions, and we said, what is the chance this student that you just randomly met was 20 to 21 years old? And so based on the relative frequency, where 35% of the students at the school are in that age category, I would say, oh, there's a 35% chance. Guess I wanted to write something there. There's a 35% chance that student was in that age category. And then what's the chance the student is at least 18 years old? So what I could do is I could add all these up, or alternatively, since I know only 3% are below that, I could say, well, it's 100 minus 3, 97% chance that student is at least 18 years old, right? There's a 97% chance. It's only 3% of them are younger than that. Now, we could ask similar questions to those if we talk about it from the perspective of probability. So, let's look at the same group, but this time let's say, what is the probability that you have a student that's 22 to 23? So in that case, when it's specifically talking about probabilities, we're going to want to use the decimal value. So what's the probability the student is? Again, based on the relative frequency, I would say there's a 0.25 probability that student is, or in other words, a 25% chance, right? Or alternatively, I guess I wanted to do this. What's the probability the student is younger than 22 years old? So again, you could do, if I want to be younger than 22, I could figure out what it is to be 22 or older and then take 1 minus that. In this case, it's probably just easier just to add these up and get 0.68. But, you could see, oh, that other one also works out to be 0.32, so what do we say? This one is 0.25. So basically what I'm trying to get at is when we talk about percentage chance of something happening or probability, they're kind of the same idea. It's just your presentation when we talk about probabilities should be in the decimal form. But they're basically the same kind of idea. All right. All right. So go ahead and do the problems 5, 7, 9, 13, and 14. Pause this video, take care of those, and then come back. Okay, so you're back. So let's talk about some more about probability notation and how things are going to be discussed with probabilities. So you're going to see some notation like this. Probability of, let's say, A, probability of something. And this is how we're going to talk about the probability of that event occurring. probability of an accident, so it'd be probability of, and then have accident in there, or probability of getting a job. So you say P parenthesis getting a job in there, that kind of thing. And then if you're told that the probability of this event is 1, that means it has to happen. Because remember, probabilities are the percent chance it would happen as a decimal. Well, 1 as a decimal is 100%. So if the chance of it happening is 100%, it's got to happen. It's got to happen. What's the chance that the sun is going to be rising in the morning? Well, it's 100%. What's the chance that every one of us is one day not going to be alive? Well, it's 100%. So it's going to happen. Now, some people might say, well, no, who knows what's going to happen with the sun tomorrow? Effectively, it's 100%. All right. If you're told the probability of an event is 0, that means it's impossible for that event to happen. There's 0% chance it would happen. So probability of something happening is 1, it has to happen. Probability of something being 0, it can't happen. What's the chance I take a math test and on that test I get both an A and a D? Well, that would be a 0% chance. You can't get both an A and a D on a test. You either get an A or you get a D or you get some other letter, but you can't get 2 of the same grade or 2 different grades on that one test. All right. The complement of an event is the event that the complement of event A is the event that A does not occur. So it doesn't happen. I'm not, again, sorry, you can't read that. But so if you take the probability of something happening and the probability of its complement, which is it doesn't happen, that always has to add up to be 100%. So there's a certain chance it's going to happen. There's a certain chance it's not going to happen. And together that makes 100% every time. So it's always got to add up to be 1. Which means we can move things around and say, well, if I know the chance that A will happen and I want to figure out what's the chance it won't happen, I can always do 1 minus the chance it doesn't happen. That's the complement. So if you think about earlier in this video, I said, what's the chance that someone's 18 or older? Well, what you could do is we could say, well, if we know that there's a 3% chance or 0.03 probability that they're younger than 18, you could do 1 minus 0.03 and get 0.97 or 97% chance they're 18 or older. That's this concept. And this is going to show up a lot. Sometimes it's easier to figure out, instead of figuring out a certain event, you figure out the complement of that event. And then you do 1 minus that, or vice versa. So, maybe we know the chance of something happening and we want to figure out the complement of it, or maybe we know the complement of it and we want to figure out its chance. You can always do 1 minus that. Because again, these have to add up to be 1 or 100%. So if you know one of them, you can figure out the other one from that. Okay, so how do we come up with the chance or the probability of something happening? So one way, kind of what we do on an everyday basis, is we just use our intuition and past personal experience to figure that out. So I'm a math teacher. If I have a student who has failed every single test in the class, and then we come to the final and they go, what's the chance I will get an A on the final? Well, it's probably not 0. Maybe there's reasons they failed every test up to that point. Maybe they had a job and their work situation has changed, giving them a lot more time to study. Maybe there's certain concepts that they've been struggling with that suddenly clicked into place. Maybe they were just purposely trying to do poor, for some reason. And then they thought they would just, do a rope to dope at the end and, ace the final. I mean, all of that could happen. The fact that I've never seen it happen leads me to believe the probability of that happening is so small, it's almost 0. So I'd probably say, if a student asked me that, what's the chance I get an A? I think well, maybe a 5% chance. 5% chance you'd actually be able to do that, 0.05, probability. Basically, I'm saying it's not going to happen, but it's not exactly 0. Maybe there's some weird thing that happened that it could happen, but I wouldn't bet on it. That's not the way I would do. So we do this all the time. What's the chance based on our experiences? A second way is kind of what we did on the that earlier example with the college is you base it on relative frequencies. And so just a reminder of how you calculate relative frequency. You say, what's the frequency of that particular event divided by all the possible uh, things in that thing. So what's the frequency of that class or, a particular event, and then divide it by the number of every item or observation in there. And you assign it by that. It's like, hey, 3% of the students are younger than 18. The chance I'm going to run across somebody who's younger than 18 is a 0.03 probability. It's 3% chance I'm going to run across one of those. Basically, 97% of the time, the people I run into are not going to be younger than 18, but 3% of the time they will be. And then the last one is oftentimes in situations where we kind of know individual probabilities and we want to find the probability of a specific event. And so what we do is we look at all the different ways you could get that particular event you're looking for out of all the possible events that could occur. So we're going to look at a coin flipping example. And so you'd say, okay, well, how many ways could I get this particular event out of all the possible outcomes of flipping these coins? And that would give me the chance that would happen or the probability that would happen in that calculation. So, this is more, instead of actually going and doing the experiment, you just theoretically think about, if you know the particular probabilities, figuring it out. Okay, law of large numbers. And this is one of those concepts that, a lot of calculations, like if I say, how do you calculate variance 2 years from now, you may not remember. But if I said, you know, this idea, this general idea, whether you remember the exact wording of it or not, you have an idea of what it is. And so what this law of large numbers says is that as you increase the sample size, so you take a sample, you get relative frequencies based on this sample. What we're going to find as the bigger that sample size gets, if I sample 10 or if I sample 1,000, the 1,000 one is going to get closer and closer to what theoretically the probability should be, or the actual probabilities in the population itself are. And so but remember, our goal here of doing samples is to kind of tell us something about the the population. And so as if I want to say, what's the chance, my tire is I'm gonna get a bad tire uh from this company. If I look at 10 tires, I might not get a bad tire. But if I look at 10,000 tires, it's going to give me an idea of how often this certain brand or company's tires fail. They don't, they just, they're not good tires. And so as I get bigger and bigger sample sizes, I'm going to get more and more close to that actual probability, especially if those probabilities are very small. You may not see something if your probability is very small in certain samples until you get such a big sample that you eventually start to see it. So that's what this is saying. As the sample size increases, the relative frequencies are going to get closer and closer to what those actual probabilities are, what we think those actual probabilities should be. Another way, this kind of like the reverse of that, is that probabilities are not great predictors for small trials, but they do for large ones. So if I had a die, a 6-sided die, and I said, what am I going to roll on this die? This next time, am I going to roll a 1? Am I going to roll a 2? Roll 3? You're only going to be right 1 in 6 times, right? But if I said, let's say I have 600 dice, and I roll them, and I said, about how many of those are going to be ones? And you say 100 of them, that's going to be pretty accurate. It may not be exactly 100. It's probably going to be like, 93 or 120, but it's going to be pretty close to 100. Of those are going to be ones, assuming the die is fair. It's not a weighted die or something. So you can make predictions about large groups where you can't really do it with small ones. So the larger the sample size, the larger you're looking at, the better these probabilities are going to line up with the relative frequencies. So like the example I used is like, let's say you had a multiple choice test, and it had 4 possibilities, and I said, about how many should be A? Well, if they're randomly chosen, assigned, about 25% of them should be A. Now, let's say you took a test and half of them were D and only 10% of them were A. You say, well, is that correct? And I'm like, no. I mean, that can happen. That can happen with a random assigning of, which answer is correct and which one's not. Then you say, well, I thought it was supposed to be 25%. Well, yeah, on that one test, it's a little off. But what if we look at every single test that uses A, B, C, and D, that where it's randomly assigned for an entire year from every single class from every, in a college, and what you would see is it would work out to be about 25%. It'd be very close to that. Whereas that test you had a lot of D's, maybe on another test you have a lot of A's, and it kind of balances itself out in the long run. So that doesn't mean you're wrong about that probability prediction. It just means on a given sample, you may not see it perfectly match up. Okay, so go ahead and do problems 1 through 4, pause the video, and then come back when you're done with that. Okay, so I'm assuming you're back here. Let's go on. So a statistical event, again, and I gotta fix this so it's not all blocked here, but any random activity that results in a definite outcome. So this is a little bit of vocabulary, kind of understanding when they're referring to things. So if they say I have a simple event is one particular outcome for a statistical experiment. Okay. And again, we're going to look at an example of this and make it a little bit clearer. But you have one simple event, and then you have a particular event. And a particular event is when you collect all the simple events that fit that particular shared feature that we're looking for. That's an entire event. And again, we'll look at an example of what we're talking about. And then all of that goes into the sample space, which collects all of the simple events that could occur. So the sample space is the set of all the potential simple events that could occur. So let's see if we can kind of make those phrases or those expressions make a little bit more sense. Try to click onto something. So this is what I was talking about. Let's look at a situation where we flip a coin twice. Okay. A possible simple event that could occur is you could get heads and then tails. So that's what this means when you see H and then T. The first coin flipped, we got a heads. The second coin flipped, and we got a tails. Okay. So that's one particular simple event that could occur. So what would be an event then? Well, an event might be I'm looking for getting one tail on 2 flips, getting exactly one tail. And so how could I do that? Well, I could have heads and then tails, like we did with that first simple event, or I could get a second simple event, which would be tails and then heads. In both of those cases, I have one tail and one head, but more importantly, I'm looking for one exact tail on 2 coin flips. And these are that's the event. And these are the simple events that make up that event. And then the sample space would be all the possible outcomes you could get from flipping 2 coins. So you could get heads and heads. You could get the heads and tails that we talked about earlier. We could get the tails and heads again that we talked about earlier, or you could get tails and tails. So, what we see is this makes up 2 out of the 4 in the entire sample space. And if all I want to know is, well, what's the probability of me getting one tail, exactly one tail on 2 coin flips? That's a 50% or 0.50 probability, right? Because it's 2 out of the 4. So 2 divided by 4, the probability of it occurring. Remember, that was the way we could assign probabilities, is the frequency of that outcome or that event in this case out of the sample space, all the possible outcomes you could get. Okay, so this is just if you've looked at Venn diagrams, it's kind of a Venn diagram of those concepts. So you have the sample space is the big box, the entire box, everything inside. The circle shaded, pink shaded or red, light red or whatever area is event A. And then the blue shaded area outside of that, still within the box, is a complement or event A not occurring. So, we would say in this case, on the previous example, maybe do heads and tail or tail and heads would be in there. And then outside of that, the complement of that would be heads and heads or tails and tails. right? So, and then the sample space would have all of that, right? Heads and heads, tails and tails, heads, tails, tails, heads. That's entire sample space. All right. Okay. So go ahead, finish up this assignment. 11, 17, 18, and 21. Don't pay attention to that. It's not homework number. That's an old thing. But 11, 17, 18, and 21 for 4.1. All right. Have a good day.